Hello all, my name is Akash and today we are going to explore a fascinating topic, how to solve an ordinary differential equation using modified-Euler's method in MATLAB. So let's understand what is modified-Euler's method. This numerical method is the advanced version of Euler's method. This method is developed to generate more accurate results than that of Euler's method. This method mainly follows two steps for solving the differential equation. One is predictor step and the other is corrector step. The formulas for the two steps are shown over here. The predictor step uses the formula of Euler's method to calculate the value of y, and then the corrector step uses this value of y in the formula of modified Euler's method to calculate the more accurate and corrected value of y. Now we will move on to solving the numerical analytically using modified Euler's method. So this is the given example. We have differential equation dy by dx is equal to minus xy square and y is equal to 2 at x is equal to 0. We need to calculate y at x is equal to 0.2. Here h, which is step size, is given as 0.1. Consider the initial value of x, that is x1 is equal to 0 and y1 is equal to 2. So as h is given as 0.1, we have x2 is equal to 0.1 and x3 as 0.2. So starting with the predictor step 1, we have used Euler's method formula here. Y of n plus 1 is equal to yn plus h into f of xn yn to calculate the value of y2. So substituting all these values of x1 and y1, we get y2 as 2. In the corrector step 1, we have used this y2 value from predictor step into the modified Euler's method formula. So here in this step we will calculate the corrected value of y2. Now for first iteration, we have used this formula with n is equal to 1 and m is equal to 1. Putting the values of x1 y1 and x2 y2, we get the answer for y2 as 1.98. So this is the value for first iteration. Now we will perform second iteration using this corrected value of y21. We will continue doing iterations until the y value starts repeating itself. So substituting this y21 value in this formula here, we get the y22 value as 1.9804. Then use this value of y22 in third iteration over here and you will get the value for y23 as 1.9804. As we can see, the value of y2 is repeating itself. So here we stop doing iterations and the final corrected value of y2 at x is equal to 0.1 is 1.9804. We need to calculate the value of y3 at x is equal to 0.2. So moving to predictor step 2, here we will repeat all the above steps only by replacing n is equal to 1 with n is equal to 2. So using this Euler's method formula and substituting the values of x2 and y2, we get the value for y3 as 1.9412. Further in the corrector step 2, we will generate more accurate value of y3. Now we are calculating y3 at x3 is equal to 0.2 using this modified Euler's formula. So doing the same procedures and substituting the values of x2 y2 and x3 y3, we get the value of y31 for first iteration as 1.9231. For iteration 2, substitute the recent value of y3 into the formula here and you will get the value for y32 as 1.9238. Moving on to the third iteration, substitute this value of y32 in the formula here. You will get the value of y3 for third iteration as 1.9238. So as we can see above, the values of y3 are repeating itself. So we stop doing iterations here. We have got the value of y3 at x is equal to 0.2 as 1.9238. So here is the final answer for this numerical. And now we will move on to implementing modified Euler's method in MATLAB. If you are watching this video and have not subscribed to our channel, we request you to subscribe to our channel. So starting with these commands, these are all the standard commands used to clear any previous data in command window and workspace. Next, in this section, we will take inputs from the user for the values that are given in the question. Here we use input function to take the differential equation as the input and we store this equation in the variable name f. Then we take the initial value of x, that is x1, initial value of y, that is y1, the value of x at which y is to be calculated, and then the step size h. We assign all these values to the respective variables a, b, c and h. In the next part, we store the differential equation in the variable name func, that is func. Now this func becomes the anonymous function as the user have inputted the equation in the format like this. At line number 23, the range of x, that is 0, 0.1 and 0.2 is assigned to the variable x. This command stores the value between a and c, including a and c. The values between a and c increase by a difference of h, that is 0.1. The initial value of y, which is stored in the variable b, is now assigned to the variable y as its first place value. So the first value in y matrix become 2. Moving to the next part. Now this is the important part of the program. Here we have used two for loops. One is outer for loop and the other is inner for loop. In the outer for loop, we have used the syntax I is equal to 1 as to length of x minus 1. So the length of x means that the number of elements in matrix x, which is 3 here. So the value of I becomes 1 as to 2, which means this outer for loop will execute for 2 times. As we have discussed in the analytical example, we first use the predictor step to calculate the value of y using Euler's formula. So the Euler's formula, y of n plus h into f of xn yn, is assigned to the variable y underscore predi. Then moving for the corrector step, we have to perform iterations to calculate the corrected value of y. So here I have used 3 iterations because the y value starts repeating itself after 3 iterations. You can use any number over here. The modified-Eulers method formula is assigned to the variable name y corrector. This formula is y of n plus h by 2 into f of xn yn plus f of xn plus 1 yn plus 1. In modified-Eulers method, we need to use the most recent value of y in the upcoming iteration. So we have used this command over here, which assigns the recently calculated value of y corrector to the variable y predi to be used in the next loop. So here the inner for loop ends and this last command assigns the value of y corrector that is calculated from this above loop to the y variable that is going to be used in the next loop. So this loops executes in the manner as first this predictor step 1, then this corrector step 1 with its all 3 iterations, then updating the value of y to be used in the next loop. Again for the second loop, this predictor step 2, the corrector step 2, 3 iterations and then end. The next section at line number 42 is used to calculate the final values of x and y at respective points. This step stores the x1, x2 and x3 value in the matrix form within this variable named x values, and this command stores the y values in the variable named y underscore values. This step is used only to collect all the output values of x and y at one point and show them in command window. Moving to the last part of the program, this plot command generates the graph of the final results. To understand this part, we will execute the code. So here we will first enter the equation in this format @xy space minus x into y square. Then we will input the initial value of x, that is 0, initial value of y, that is 2, the value of x at which y is to be calculated, that is 0.2, and the step size h, that is 0.1. Press enter and you will get the values of x, y value and this graph. So these are all the final values of x and y. All these values are plotted on this graph. These commands over here just add supporting parameters to the graph. The title function gives title, x limit, y limit, gives the range of the x-axis and y-axis from here to here. The x label and y label provides the name to the y-axis and x-axis. So this was the MATLAB code for solving ordinary differential equations using modified-Euler's method. You can test this code by entering any equation, any x, y and h value over here. So I hope you liked the video. Thank you for watching the video. Do like this video if you found it helpful. If you have any queries, post them in the comments or get in touch with us. Follow us on LinkedIn, Facebook and subscribe to our YouTube channel. Education is our future. MATLAB is our future. Happy MATLABing!